Welcome to Baffin Bay off the coast of northwest Greenland. I'm Beth Doyle.
And hello, I'm Michelle Pratt. We're outreach officers on board the Joyde's Resolution for Expedition 400. Today we're sharing with you an open house recording that we led about a week ago, and we've also supplemented with a couple additional recordings from where the internet dropped on the tour. So we hope you enjoy the tour.
Well, hello, everybody. Welcome to Baffin Bay. Hope you enjoy your glimpse of life in Baffin Bay and the Jody's Resolution. So I'm Victor.
I'm Paul.
Paul. Yeah. We're ice navigators. I'm retired Coast Guard captain, Canadian, and Paul.
No, I'm still sailing. I've been sailing for about 38 years, the last 20 with most of my time in the Arctic and the Antarctic.
What are you looking at today?
Well, today we're here supporting the captain and his team to stay safe in the polar waters that you described earlier. So, yeah, we're literally here as you speak on the radar, checking out 3 of the icebergs in the neighborhood. We have Fred, which was just up the way, which we've been, almost 3 weeks in proximity to this one iceberg, and it is a very large iceberg. And it's kind of neat. So we'll get to see it a little later on today. Yeah, and we're watching for bergy bits and growlers, all the tricks of the trade.
The bergy bits and growlers. We've heard about these. We might have questions for the ice navigators. Definitely, we can follow up and give you the information that you're wondering about. Thank you so much, gentlemen. And now we see the captain. Hello there, sir.
Good morning, afternoon, evening, wherever you are. Welcome aboard the vessel. I will take this one.
No one can hear you.
Absolutely.
Excellent. There you go.
All right. Well, welcome aboard of my ship. Or our ship, actually.
Wonderful to be here. Can you tell us a little bit about what you do?
As little as possible. Well, most of the time I spend on the bridge, obviously. And right now, the ice navigators that you just talked to, they make my life very easy because they take a lot of my work out of my hands. So it gives me more time for administration, paperwork, procedures, all that kind of stuff. Making sure everything runs smoothly. If somebody has a problem, they can come to me, talk to me. I'll try to find a solution. And that's basically my job in a nutshell.
Excellent.
Sounds simple, right?
Anything unusual about Arctic waters?
That's cold. That's now the unusual thing we're having is obviously the icebergs, monitoring the icebergs, which Victor and Paul have been doing for us. And that creates some issues if they actually come up close. We're attached to the drill floor with a drill string. If they do come up close, we'll monitor them. We have certain procedures to follow. If they come close, we actually have to pull up the drill string. That might take several hours. So we can't just move out of the way once you're attached. So that's pretty much a challenge over here, these icebergs. And they're rather unpredictable. They don't go in straight lines like a regular vessel. You can't call them to ask them to get out of the way like a regular vessel. And I've seen icebergs that literally turn around the ship. And we keep an eye on that. That's the biggest challenge over here, basically. Make sure we don't get hit by them.
Terrific. Thank you so much, Captain. Appreciate
You're
it.
very welcome. And enjoy the rest of the tour.
Excellent.
There you go.
We are moving on, talking about the mission, the scientific mission. And with that, we are joined by the co-chief scientist.
Oh, yeah. Hello. Hi. My name is Paul. I'm a marine geologist at the Geological Survey, Greenland, Denmark, and I am here as a co-chief scientist together with Anne.
Nice to see you all. I'm Ann Jennings from the University of Colorado at INSTAR. And Paul and I have been working on the planning of this for years. And this has been a fabulous adventure for us and very successful, we think. We're here floating over what once was the Greenland ice sheet that repeatedly advanced across the continental shelf. And it's left a sediment record of its advances and retreats through time. And we're here to investigate how the ice sheet advanced and retreated, what was forcing that, how it's responded to past climate warming and cooling, through millions of years.
Yeah, and I can just add to that at this point in time, we have been really successful. We have actually achieved all our scientific objectives, including getting over 2 kilometers of sediment core out of the continental shelf here. So we hope that will take us, we know it's going to take us way back, millions of years back in time, and we can use that information to understand how the ice sheet has responded to climate warming in the past. That is one of our ultimate goals with this mission.
That's outstanding. Well, it's great for our viewers to hear the big picture, what you've been up to. What we'd like to do now is to head outside to the lifeboats and the drilling rigs and give people a sense of how this floating laboratory works.
Go.
Okay, we are outside now, and it is a brisk morning. You can see snow on the lifeboats here, and you're looking at one of our 4 lifeboats. Each lifeboat holds 70 people. We have about 117 people on board, so easily enough room for each person in the lifeboat. It has a GPS system. It has emergency rations for over a week. It has a navigator would be on board with us with a rudder. We would wear our hard hats and goggles, and if we needed the restroom, well, that's what your hard hat is for. If you get seasick, that's what the hard hat is for as well.
All right, and now we're going to learn about one of the most distinctive features of the JOIDES resolution, this amazing drilling derrick. And so let's walk over and meet Bill and learn more about the drilling operations here on board the JOIDES resolution. All right, so here we are today with Bill. And Bill, what can you tell us about the drilling operations on the JOIDES resolution?
All right, we're coring right now. So we're in operation of retrieving a core at the moment. Behind me, you can see the derrick, 192 feet above the water line, rig floor, and the activity behind me. What we do is we screw together a series of steel pipes called drill pipe. Those extend all the way to the drill floor. Then we lower a receptacle down, we call it a core barrel, to collect the core and bring that back up on some steel cables that you can see turning on the winch over here. So we do that over and over. We'll pick a barrel up, we'll get the core out, we'll put another barrel down. It's kind of a end over end thing with a core barrel. It's much quicker that way than trying to retrieve this pipe several hundred meters up and get a core. So the pipe stays down and the cores come back and forth. And it's pretty much a 24-hour operation while we're doing this.
Excellent. And can you explain to us what's happening right now? I see some equipment moving behind us.
Yeah, what they're doing right now is they're breaking, they call it breaking a connection. They're unscrewing a section of the pipe so that we can get the core barrel, the core receptacle out in between. Once he breaks this is a iron roughneck they're using to apply the torque. It's quite a lot of torque to unscrew that. It's not like a bottle cap. It takes quite a bit more. So they'll unscrew it. The driller in the cabin behind them, behind the window over there, will unscrew it further. And then we should see a core barrel on a steel cable if all's going well.
Great. Well, let's hang out here for a couple minutes and see what we see. Okay, Bill, talk us through what's happening with
All right,
this.
they're retrieving the core barrel from the pipe. They're disconnecting it from the cable, the winch cable that runs it up and down the pipe, and they're going to put it on a separate winch that pulls it free of the pipe. You'll see a core barrel come up here in just a second. So he's releasing it there. So they move the drill pipe out of the way, and here comes the core barrel, hopefully with core inside. And we can see just how long these things are. They're about 10 meters long. They'll move that over to a small working area over there while they connect a new piece of pipe to then connect and run a new barrel on. That has some core in it.
Excellent. All right, so this is really, if we just pan up for a second, this is really where this very tall drilling derrick comes into play, because we need all this space to be able to move vertically with these large sections of pipe.
All right, what they're doing now is bringing the core barrel over that they just removed. Hopefully has core in it. They have to lay it down and clamp it in the vise, and then they remove the end so that we can get to the plastic liner and the core. And this is something they could do in their sleep.
So, Bill, this is a very experienced crew from what I understand. People have asked if it's different people every time, and while we do have different shifts, there's one group on this ship and then another on the next expedition. This group really has been doing this a while.
Yes, they have.
Yeah.
They're probably close to 100 years overall on just the one shift.
Wow, that's an incredible lot of experience just in drilling technology and in understanding the mechanism for coring and what's going to be most successful in recovering this scientific material.
You can see some core in there.
So you'll also notice one of the science techs is ready to receive this core.
Yeah.
So this is where the drilling crew really hands off the material to scientists.
Yes.
And let's see.
Yeah. He's going to take the core catcher portion first, and then we'll have a whole liner come out.
Okay.
And hopefully with a lot of core in it, or at least some core. That's not one of our better ones. It's about a meter, a little over. That's not one of our better ones right there, but sometimes that's all we get.
All right, so Bill, thank you so much for sharing this drilling operation and the mechanisms on board for retrieving scientific cores from beneath the ocean floor.
Oh, you're very welcome. Thank you.
Great.
All right, live again. All right.
Life on a ship.
Yeah.
Internet is fun. It's actually quite amazing, the internet that we do have available. All right, so Bill, can you keep telling folks what happens around here?
Yeah, we're board and comes in the plastic liner. Here's a big sample, although that one's a little shorter than normal. But imagine it's full of core. A lot of excited scientists, and the first thing they do is take some measurements, and then they'll cut this into somewhat of about 1.5 meters pieces. They call them sections. So they'll split the core up into small sections. Only way we can handle it to get inside. And it pretty much lives its early part of its life in this core liner, as you see going through the lab later. So a lot of activity out here on the catwalk. Everybody likes to hear the core all day inside.
Great. And Bill, I'm wondering if you can show us a drill bits up close.
Yeah.
So, like you were mentioning, the bright silver drill bit.
Bright silver bit is the one closest to the table here. This is the little sample we leave out here. That is one of our RCB bits, rotary coring bit. It's one of the original systems with the program. The big roller cones you see here with the tungsten carbide teeth, they actually do the cutting and bring the core up into the barrel, which we bring the barrel up on a cable. So we can collect core continuously with this. We just put another barrel down and collect it. We also have another system we've used on this expedition called it's got the APC XEB, stands for piston coring, extended coring. This one's a little different. You notice the hole is bigger. We have a piston core, which is basically a 30-foot cookie cutter that extends through here and takes the core. We also have a smaller cutting shoe that extends through here and can cut core as well. So we have a couple of different systems we can run in here. But these are typically for our softer formations. Right now we're going to be in harder stuff, so we need to run the RCB system. And I got a drilling bit here for show. Typically in oil industry, you'll see drilling bits. People ask me, well, how do you tell the difference between a drilling bit and a coring bit? Well, the coring bit has a hole in the middle, so it's really easy.
Thank you so much, Bill. Really appreciate learning about the coring technology, and I especially know my dad is going to love to hear about that. So thank you so much. If I can steal your mic from you, we're going to, there we go. And thank you so much. All right, Lisa, there we go. All right, so this is Lisa, and do you want to introduce yourself and tell us a little bit of what's happening out there?
Okay. Yes, my name is Lisa Crowder. I am what's called a laboratory officer, basically just supervisor of the technical support team we have, and just overseeing and in charge of the laboratories. So we're going to carry on from what Bill told you, and he mentioned that we cut the cores into reasonably sized pieces so that we can actually carry them around in the laboratory. So this is an example here of a section. It's 1.5 meters in length. And like we say, we measure them out from the big liner. We use some specialized cutters to cut the liner. And then we put some caps on the end because we need to know which way is up, right? So we have blue for up, like the sky, and then we have gray, or it used to be clear, like the water, right? So top and bottom. So we can always keep oriented our material. So once we cut them on the catwalk, then we need to take them inside, and we'll do one of the most important things, which is label them so we know where they came from.
Awesome, Lisa. Let's follow you inside the lab. Come on, everyone.
So we're going to put this in our favorite instrument here, which is the laser engraver. Okay, it's actually going to laser etch the information about the section. So we're going to have the expedition, the core, the site, the hole, the core, and the section. So you can watch it do, and more importantly, we can watch Laser Kitty up there. And that's Laser Kitty. Very important. Very important. And again, this is one of the most important things we can do because we need to know exactly where each piece of core and any subsequent samples come from, because that will then register that information in the depth within the hole. Okay, so that's what we do here. And we even put like a human readable label with a barcode scanner so we can use it for our instruments. And when we're coring, normally this area here, we would have a rack full of cores over here, okay, which we did yesterday, and then we processed them all. But these racks can get filled up with a lot of core, okay, thousands of meters of cores as it cycles through the laboratories. So after we've done all the labeling, we're going to pass it off to scientists who are then going to start doing their measurements. So, excellent. Thank
Great.
you.
Thank you so much. Okay, so we're going to do a quick switcheroo. Here you go, Laura. And Beth, I'll have you take over.
Excellent.
Let's switch it up here. Beth, you're going to need a mic as well.
Thank you. Don't mind if I do,
Okay.
just temporarily. I'll get it back to you in a bit more. Okay, we're here with Bob. Why don't you tell us?
Yeah, so I am a critical property instrumentalist on this expedition, and I'll show you one of the instruments that I work with. So you see this core, so that's a cylindrical core. This is what we extract from below the seafloor, and it consists of a lot of mud, some sediments, sometimes rocks. We have these labels put on these cores so that we can identify them, and then this information can be uploaded in the system. So I basically scan it, and then I measure some physical properties on this core, and these physical properties, they help us to distinguish between different types of sediments and rocks. So this instrument, it measures three types of physical properties. This one is it's measuring the bulk density. Now, what it is, it's basically if you have a piece of foam or thermocol in one hand, and if you have a piece of rock in other hand of the same size, you'll feel the difference in the weights, and that's because of the difference in the density. That's what we are measuring here for the core sample, and it's because different layers of Earth, they have different densities, and this helps us to distinguish between those different layers. This white colored instrument, it measures the magnetic susceptibility. Now, every sample or every sediment, it has some magnetic materials inside it, and how much magnetic material is present, this is what it measures. Next one is the P wave velocity. So basically what I'm speaking right now, I'm generating P waves from my mouth. And when these P waves, they travel in different layers of the earth. So we are firing P waves in the sediment. And when these P waves travel in different layers, it helps us to know about how fast the wave is traveling or how slow the wave is traveling, and helps us to again distinguish the different layers of the earth. Next one is the thermal conductivity. So you see this coffin type box. We put this ore in this box and we measure the thermal conductivity, which is basically how much heat a sediment or rock can pass through it. Now, Earth has different layers from crust to mantle to core, and the core is constantly generating heat that is flowing through the different layers up to the crust and going out. And this helps us to know how much a specific sediment or rock is passing, how much heat flow it's passing, and that is useful for scientific analysis. Now,
Thank you.
yeah, I pass it over to Lara, who will explain you about the AGR measurements.
Yeah. Hello, everybody. So, how is your Saturday going? We keep working here on Saturdays and weekends, and I'm going to show you. Host was saying we are measuring different things, and since he spoke about many different properties, and I'm going to keep doing that. But first, I want to show you this super amazing machine we have here. That is our X-ray, and I'm pretty sure that most of you have gone to the doctor and have an X-ray of your arm or your leg when you break up bone, right? Well, here we do the same to the horse, and we don't see broken bones, luckily, but we see when they have some more pebbles or some rocks that they are inside our cell. We can see many things. Sometimes we even found corals, hotel corals, and things like that. So that images, you are going to see some of the ones that we identified later on over the description tables. But I want to keep going with the physical properties. And we have another yeah, that is the NDR, it's the measured natural gamma rays. As you know, in nature, there are some elements that produce gamma radiation, and like potassium, thorium, and uranium. And this measure this radiation from the natural detector. We press a button and it's like magic, but it's called engineering, and it just goes in and it starts to measure some of these element properties. Now you can see the different curves coming down that are just how these elements are generating this gamma radiation we talked about. So when we have this gamma radiation measure and also the densities and velocities that Host was talking about before, we put them here in this computer. And here we have a software that is called Correlator. And it serves to allow us to put all the pieces together because we have the different measurements that they form curves, and they are kind of in pieces. They belong to different cores and different sections, and we don't know how to fit them together. So that's what we do here. We put all the pieces together and we create something like what you have here that summarize all the densities and velocities and the radiations that we were talking about. And after we do that, we are ready to split the course. And for that, I pass over to Lisa that is going to explain how we split the course in two halves.
Right, great. So yes, we need to split the course, so we go in the splitting room. We use saws sometimes, so we have to have doors. We have two ways of splitting. Right now, because we have harder material, we're going to use a rock saw. Now, this saw is just like the kind of saw that you might cut tiles for your floor. Okay, it's just a rock saw, and then we have a nice joystick that we can run the cord through there. When it's softer, we use a different system, which is basically a cheese cutter. We use a wire. It's a wire and some blades to cut the liner, and then we just run it through bottom to top, and then we get two nice equal halves, which we're going to call the working and the archive. And I'm going to go see them.
So you saw the whole core analysis, and then there's the splitting so the scientists can actually see what is inside.
When we come out of the splitting room, we're going to put the working half of the course here. And we're going to take the archives and put them over here. And then we'll let Tracy and company explain those. But on the working half, what we're going to do is actually do some of the destructive sampling. Here you can see this table is ready to do some sampling for paleomagnetics. Alex will talk to you about that. And the samples go in bags, and they have, again, more labels because we need to know exactly where they came from. And this will all correspond to depth within the hole. Okay, so on to core description.
Hi, everybody. Welcome to the core description lab. This is where the core comes next, and I think Lisa just explained that they cut the core in half, and part of it we can take samples from, and part of it stays pristine, and this is what we call the archive half over here. So our group has the responsibility of describing and characterizing all of the cores, and we do that in a number of ways. We use some machines that you can see over here. So we have this machine here that takes a high resolution digital image of the core, and it also measures the color of the core. That's more consistent than we can do with our eyes. And then in the background, we have another machine there called the schnizzle. We schnizzle our cores, and that measures magnetic susceptibility, and it also provides another measurement of color. And the other machine that we use is an X-ray instrument, and we create X-rays of the cores that allow us to see what's inside the sediment. And you can see an example of some X-rays in particular. But the most important thing that we do is pretty old-fashioned, and that is sitting and taking our time looking at the core and describing the core. And I'm going to hand things off to Sandrine for that.
When we are describing the core, we are standing there on the table with all the section of the core, and we have paper sheet like this that help us to describe the color, the variation of color in the core, but also the kind of sediment. We have sand, mud, glass, the structure, the sedimentary structure. If we have geometry that we can see on the sediment, and with this and the X-ray and the measurement we done, what Tracy showed you, we can try to understand how the sediments were deposited in this environment. So here, for example, you have change in color. So we have color charts like these that can help us to define the color of the sediment. And on the table, you have beautiful example of variation going to brown, light brown, dark brown, to something which is more gray, green, and different kind of sediments with glass. You see the big glass in the sediment that probably come from the melting of ice that drops down into the seafloor, to very fine sediment where you barely see the grain. So it's our job to try to define and understand why those different sediments appear here.
Thank you, Tracy. The image of the core here, so very uniform, but there's a lot of detail here, isn't there?
Yeah, we have some magnetic here to really look into some details. That you will see that here you have some grains, some pebbles, so we need to know if they are coming from the volcanic rock or if they are carbonate. And also sometimes we can see some shell fragments which are very tiny or broken, so we need to be very close to the sediment to look at it.
I'm kind of intrigued by this X-ray here with little curly cubes.
Yeah, those
tell
are
us anything?
burrows.
Those are burrows.
So it's biotubation. It's something that you can see a bit here with this patch of lighter color.
but you have to know it is, and mainly with the X-ray Z pop up like very strongly on the X-ray. That's why we are doing X-ray to unravel some features that are hard to see with their eyes, and those are really nice burrows of the sediment.
Thank you so much, Sandy. Hello, Lisa. Hi. Lisa. I studied field in the past, field. So, how does that help us here? Well, it's because right now field is going straight down. So the situation is normal. So it, and then sometimes, like 800,000 years ago, it was going straight up. And you know when all the pencils happen, all those clips of the field happen, and so it can measure the magnetic direction in the mud and map it for a bark place here. Then you can tell how old the sediment is, and it's one of the ways that we've been really relying on several so we measure it by keeping the core in one of the ways we do it is by sticking the core in this magnetometer and send it to go bye-bye. And it goes in there, that's the time it comes out, and then we know which way the magnetic field is going in the mud. And so whether it's up or down, and another thing, Alex likes to tell you.
Sometimes we have to measure stuff in higher details, so we cut discrete samples. In order to do that, this is a bit more of the mundane tech life. It's going to change here real quick. Let's take you all to the splitting room where the magic happens. So we have to cut samples into little cubes, and in order to do that, we have to wear a proper safety gear. So I'm changing my boots here like Mr. Rogers. All right, so come on this way. We're going to go change out, put on my safety glasses. So a big part of what we do as technicians is cutting mud. It's fairly mundane, but we have to sort of keep track of everything. So we have systems in order to do this. You've already seen this in a bunch of sections laid out for sampling. We have a mark with the up arrow, so we know what the up arrow was in the hole. And then we take the sample, put it on the cutting board, container, and then we leave a little tag with it so we know where it came from. And we go in the splitting room. So if you want to follow me, we'll go in there right now. So in here, if you want to come all the way in, you're welcome to come in. We're not operating saw, so you don't actually have to be wearing your safety glasses. We have a parallel blade here. So we take the full sample, put it on that way, and the two saws cut at once and cut it into a swath like this. So we have a little wedge that still retains the marking arrow there. Then we take that piece and put it on perpendicular to that, and it comes off as that little guy. And that little guy goes onto this saw and a little jig that holds it correctly. And we chop off the end and we end up with a beautiful little cube with the arrow on it. That cube then goes into the sample jar. And then we go back out. And again, this is where it's key to have very good organizational skills. So if we put the puzzle back together and correct orientation, put a spacer in,
And normally I have two hands to do it, so I do a little bit better job.
Here, let me help you.
Thank you.
Yep.
Yes, notice the bottoms are always marked with the blue ink as I shuffle them.
Most boxes.
Left is up.
Left is up.
Left is up.
So then it's all happy back in this normal position. We take the last little bit of sample, it's a sub-sample. Goes in the jar, and now we're done with that one. So,
A lot of stuff.
a lot of steps there, and a lot of us are gonna be looking for work in the near future, so, freelance technician. we'll hire.
He knows his stuff. Hireable. He's good. Stuff. Excellent. Thank you, Alex.
You're welcome.
Hi, everybody. You are here with a crowd of people. We'd love to know what you do, what your specialty is, what you're looking at.
So we're in the Paleo lab now, so it complements all the other kind of analyses that are going on. We get mud samples from the course, and we've got various different sort of specialists here and different author groups that we are working with, and we kind of process the samples and see what kind of authors we've got. So this station is devoted to a certain type of fossil for foraminifera. So these are microscopic, well, plankton or bottom living organisms, like an amoeba, actually, an amoeba that makes a shell. So what's special about them is that they are, because they have the shell, they get fossilized. So we've got, basically, you have to look at them under the microscope. They're about the size of a grain of sand. So we can image them, look down a microscope, take pictures of them in different ways. So just here's some examples here. These guys are actually forams that have been imaged under the electron microscope.
And that's one cell.
That's one cell, and it makes this very fancy little chamber. So these guys, they make their shells out of calcium carbonate, so chalk. So they're useful for various things. They can help us with dating, the chronological kinds. So they can give us some time constraints if we find the right species. But in the same samples, we also get lots of other different interesting things. For example, this picture here is a bit of fossilized wood that has washed off Greenland. So this might have been one of the last forests or a fragment of the last forests that's been washed into the ocean. Here we've got some worm burrows that are in the cores, and they've actually been turned to gold. Well, not got real gold, pyrite, fool's gold, pyrite. So we've got lots of other things going on in our lab, though, if you would like to go down the corridor.
Thank you, Helen. Helen, manipulative specialist. We have other specialists as well. We have diatom specialists. Very different. Hello, welcome.
Hello. Hey.
He is one of our
I'm
diatom
welcome.
specialists.
Yeah, I'm a diatom specialist, and maybe we can show some. Yeah, like what diatoms are. Diatoms are like photosynthetic planktons. They are living in their siliceous shells. And then here, what we do on board, using their like fossilized shells, like we are trying to understand the paleo environment. How we do this is actually by using the very fundamental law of geology. Present is key to the past. What we observe in the present oceans and the sea floor and then the upper like part of the ocean. So what we observe and under which kind of conditions they live. By using this information, we can go back in time using our sediments and try to understand, oh, okay, these guys in the modern environments, they are living under sea ice conditions. Oh, if we see them like a couple of millions years ago and very abundant in our sediments, this might be indeed an indicator of sea ice conditions. But however, we should be careful here. That's why we are like really proud here, like using forams, dinoflagellates, diatoms. We need multi-proxy approach, like just based on only one fossil group, we can't say everything. We should combine all our information to be able to reconstruct the paleo environment and be able to like stay on the safe side. So what actually we can do a quick and what we are doing a process here for example, in real time, what we do in our day, like on daily basis. Here, one of our we see one of our samples here under microscope, and we see a small body here, like which is a resting spore of a diatom. And based on this, what scientists did is, I'm a bit messy. So they construct a like taxon range deep in time, and they based on all these expeditions like ours, they reconstructed their like geological range in the deep time. And based on this, if we observe this year in our sediments, oh, we can say that like maybe based on before like previous observations, maybe we are somewhere 10 million years ago. So this is actually the most like the foundation of our all our research here on board. But and then yeah, this is the and then yeah, in summary, our work like has like a two like main domains, and one is reconstructing the paleo environment. The second is being able to say so like in which depth we are and in which age we have in this like the latest.
Thank you so much.
Thank you so much.
Excellent.
Yeah.
We have a great overview.
Yeah.
2 micropaleontologists. We have a foreign and infrared specialist and a diatom specialist. This room is crowded, but we have one other type of specialist, and this would be represented by Mai here.
Yes.
There you go.
Hi.
And you would share with us what you do.
Yeah,
Look at this.
Yeah, so we've seen these 2 other groups. So one studies fossils that are made out of calcium carbonate, and the diatoms that are made out of silica. And I study a 3rd fossil group, and that's the group that's made out of organic materials, so organic remains. And those include a type of algae called dinoflagellates, and they produce cysts, and also pollen and spores, so they represent the vegetation. And all the information is on these tiny slides. And so we prepared our samples, we sift them, and we collect a certain fraction of all the fossils. And they're on here. And on these slides, you wouldn't tell by just looking at the slide, but with the microscope, a whole world shows itself. And we can all see all sorts of interesting things. And for example, these are pieces of plant that we see on these slides. And these pieces of plant might have been, Helen showed the wood piece. These might be pieces of the last forest that was growing on Greenland. We find these fern spores. So these are spores that are produced by ferns. So the fact that we find these says something about the vegetation that was growing. My other group that I study is these dinoflagellate cysts, these brown, cysts, and they represent sea surface conditions. Some like, for example, warm water, some like cold water, some like a lot of nutrients, some prefer to live close to ice. So we can use their abundances and the assemblage of these cysts to reconstruct sea surface conditions. And for example, this is one thing I found. These are also dinoflagellate cysts, but these are 60 million years old. So they are much older than the material that we are drilling in. And that means that they have been reworked. So older layers of sediment have been eroded off by glaciers. And that would have resulted in these older layers to be deposited into these younger layers. And that means that you suddenly see these dinocysts that are much older. You find them back in your sediments. So they show us something about how the glaciers were sort of eroding material away. And that altogether gives a very complete picture of what was happening on land, what was happening in the sea, the sea surface conditions, and then together with these other fossil groups, we try to compile this whole story of what were the environment, what was the environment, how warm was it, how cold was it, how much ice was there, how far was the ice shelf extended. That's the puzzle that we're trying to solve here. And it's really amazing. We're the first ones, the material comes up and we're the first ones to see under the microscope how this world have looked like. So that's really, it's very exciting.
That's terrific, Mike.
Yes, thank you.
What a great overview.
See our lab.
We'd love to know we are due down shortly at Geochem.
We have the best view though.
Oh, yeah, we've got to, okay, we've got to look out for them. We've got to see it. So those were the microfilm intelligence and here.
So this is where we, as Mai was just saying, we go in the catwalk and we get the first samples of the core and then we come back here and process them. So we have a few tools that help us like shake our samples and wash our samples so that we can see those teeny tiny fossils. But all the other scientists always come visit us and you think they're coming to say hi or ask you to lunch, but they're always trying to look out our window. So that's where we see giant icebergs that sometimes delay our drilling, or we get to see really awesome sunrises or sunsets, but it's really great. We've all decided we have the best lab on board.
Best job on the ship.
Well, thanks for visiting.
Oh, our pleasure. Hello. We've got a group here. Ooh, let's pass out some. A number of scientists here. What are you up to?
What I'm doing is homogenizing the sediment. Yeah, this is the important first step to for the geochemical analysis of the sediment.
So you're pulverizing it, breaking it apart.
Yeah, it's hard. So
the old mortar and pestle. Okay.
Yeah.
Who's next? Okay. Oh, got it. Hello there, sir.
Hello. Of course.
We have
So,
a syringe there.
I have a syringe in my hand.
Ah.
Well, I'm not a doctor. Well, I am, but I'm not like this kind of doctor. So, what we have to here as organic geochemists is to measure the gas content of the sediment. And this is primarily a safety measure because the sediments can actually contain quite high concentrations of methane, ethane, hydrocarbon gases. And to make sure it's all safe, we take little samples from the cores as they come on deck on the catwalk. And we put them in the oven for about 30 minutes. And then what we take is so-called headspace samples. So we take a little sample with a syringe from that void here in the vial and inject it into this instrument, which is called a gas chromatograph that quantifies the gases.
Okay, so you will look at that. What are the measurements? It's parts per thousand.
So the concentrations are actually in ppm. So this is parts per million. And we look at, so if you want to come over here, you can actually see the downpour concentration here of the previous site. And you see all these dots and you see how the concentration changes downpour. And this is due to bacterial activity of the organic matter that is sort of naturally included in the sediment. And now we have one sample here that I will inject into this GC. And if you're on your way out, you will have the peak on the chromatograph if you want to see it.
Ooh, we will check out the results. Let's pivot over here though. We have Rachel, we have Philip. They're going to be punishing some sediments with major counts per square inch. Is that right?
Yes. So what we have here is some of the sediment that we've collected on the bottom of the ocean. And what Rachel is doing is she's going to clean the outside of the sample because it came from just fresh from the drill pipe. So we're cleaning off any mud that might have been contaminated between us collecting the sample and it being in the lab. So she cleans off the outside mud and then she'll load it into this cylinder here. And then we'll put it on one of these hydraulic presses. And it goes up onto here. So you can see we already have a sample here squeezing. And what we're going to do is, so it goes up to about 30,000 pounds. So if you divide that by the area, that comes to about 8,000 PSI on the samples. And then what happens when you do that is the mud, which is a mix of minerals and water, will actually compress and the water will come out into this syringe. And so once we collect the water, we can study it chemically, which is something which Johanna is doing back here. So right now, Johanna is doing a salinity measurement. We do this with an optical instrument. So we measure the refractive index of the water, which then tells you how much salt is in the sample. And from this, we can learn all sorts of things. So one of the things we're finding on this cruise is a lot of fresh water, even though it's under the ocean. And that tells us that there used to be a glacier where we are right now, and it was a wet bottom glacier. And so this is the sample before we squeeze it. And then this is how much it compacts down. So it really, at the end of this, it goes from being like clay to being like a rock.
You were lithifying this sediment.
Getting rid of all the water.
All the water.
Making it just the dry.
Just the dry. Outstanding.
There's one more member of our team in this lab that we wanted to make sure that we introduce. So Heike is measuring ancient DNA in sediments. And it's really important when she does that we don't contaminate that with any of our really modern DNA. So Heike is in the clean room here in a very fancy suit to make sure that she is doing her work as cleanly as possible. So another very important member of this lab team.
And that suit, so that protects the sediment from her, in a sense?
From any DNA that might come from things like our hair, our faces, any DNA that might come off of us could really mix up that ancient DNA signal. So we want to make sure that none of that ends up in her samples, because that can really make it hard to find the ancient DNA among any modern DNA that could get in.
Wow, yeah, we've seen her on the catwalk in the core receiving area taking little samples there, just as interesting.
Yes, very exciting. Yes, I also got to help out and wear one of those suits for a little while, which was a lot of fun.
That's right. We have pictures of you. Well, that's wonderful. Thank you so much, Rachel. Thank you. Terrific. How are we doing for time? Anything else?
We are close to an hour, actually. So I'll follow you. All right, so thank you so much, everyone, for joining us today. We hope you've enjoyed this tour of the Dredges Resolution, this amazing vessel, as we're up in northeast Baffin Bay, northeast Baffin Bay, off the northwest coast of Greenland. It has truly been our pleasure to be able to share this ship with you and the important science that we're doing on board. Thank you so much, everyone, for joining us. We greatly appreciate it. Have a wonderful day, everyone. Signing off. Goodbye.
Goodbye.